This is the solution for the first midterm in Physics 251, Fall 2013. So I'll just work through these. Okay, so this one was kind of like a textbook problem with a train. Basically, we've got a tension pulling on 3 blocks, and there's a string between each block. The first question asks, what is the magnitude of the force on T1? We're given that each box has a mass of 15 kilograms, and they're all accelerating at a rate of 2.5 meters per second squared. Okay, well here we know that the sum of all forces on all these masses, if we just consider this one block, which is equal to, we'll say in the x direction specifically, because we know the forces in the y direction, the normal forces on all these and the weights cancel out. So the sum of the forces in the x direction, which is equal to T1, and that's it, because they're on a frictionless table, so there's no force of friction. That's going to be equal to the total mass times the acceleration in the x direction. And the total mass is equal to the mass of block A plus the mass of block B plus the mass of block C times the acceleration due to gravity. And that's just 3 times 15 kilograms. So we've got 3 times 15 kilograms, which is 45 times 2.5 meters per second squared. I've got 45 times 2.5. That's 112.5 newtons. And, you know, as long as you're right on, we could tell. So we weren't sticklers for significant digits or anything like that. So that was worth 3 points. So we gave a point if you wrote down sum of the forces equals ma. It means you knew what you're talking about. If you started sticking in other forces like friction, or somehow the normal force got in here even though it's in the y direction, that's where you'd start taking off points. But that section was worth 3 points. Now this other one says the boxes start from rest at t equals 0. How far do they travel during the 3 seconds between time t equals 1 and t equals 4 seconds? Okay, so the equation to use here would be the kinematic equation. V naught t plus 1/2 at squared. And I'd say at x equals 1 second, that's going to be equal to my starting position. I'm going to define that to be 0, plus my starting velocity times time. I'm going to define that to be 0 also. And so I'm really just left with 1/2 at squared. We know that the acceleration is 2.5 meters per second squared. And we want to know, where is it after 1 second? So 1.5 times 2.5 times 1 squared is just 1/2 of 2.5, so it's 1.25 meters. So that's where it is after 1 second. After 4 seconds, that's starting from 0. After 4 seconds, we can do the same thing. We're going to figure out how far away it is from 0, and then we're going to take the difference between the two distances, and that'll tell us how far it moved between those two times. So 1/2 2.5 meters per second squared times 4 seconds squared. Now it's at 20 meters. And the difference between them, delta x, is the position at x4 minus the position after 1 second. And that's equal to 20 minus 1.25, so it's 18.75 meters. So that was worth another 3 points. Now a lot of people, you could imagine, plug in just the difference in time. So they say, well, it's traveled 3 seconds, and somehow they're trying to compute just by plugging in 3 seconds. Well, this will tell you how far it's moved from rest if you set v naught equal to 0 in 3 seconds. That's not what we want. Okay, what is the net horizontal force on box A? Well, you could, do a sum of the forces and all this, and you know that, well, box A has mg working on it. It's got, or not doing work on it, but it's got weight and normal force, and it's got T1, and then there's the string it's towing, like all the boxes it's towing, there's a tension due to that, it's T2. But it's accelerating, so in the x direction, so we can't say that this one equals this. In the end, just notice that the sum of the forces on box A, that is the net force. So that's, by definition, that's what net means. It's the sum of all forces. We know in the y direction those are going to balance, so those are 0. This is all going to be in the x direction. We know that it's going to involve some T2 and some T1, but we know that this is always going to be equal to the mass of box A times the acceleration. So really all you have to do here is take 15 kilograms, the mass of box A, times the acceleration, and you get 37.5 newtons. And that's the answer there. So that was worth 2 points. Now, in the last one, what is the force on box B, that's the middle one, due to T3? Okay, so box B has two forces in the x direction. It's got the tension from string 2 and then the tension from string 3, because this is towing box C behind it. And then these guys in the y direction, which we can ignore because it's frictionless. Well, the thing to realize here is then to look at box C first and note that it's only got T3 acting on it in this direction. Maybe I should have drawn it on this side because it's towed behind. And we know how fast this is accelerating. We know that the sum of the forces on box C, there's only one force in the x direction, that's T3. I'll go ahead and draw these on just for completeness, but those cancel out. So it's T3, that's going to equal mass of box C times the acceleration. And it's saying, what is the force on box B due to T3? We know the magnitude of T3 from this one, so it's 15 kilograms again, times 2.5 meters a second squared. We already computed that up there. So T3, and if I want to say magnitude and direction, we weren't sticklers for this. I know this is 37.5 newtons. And I might say backwards. So here I didn't say if I wanted the vector force. So we were really just asking, for the magnitude, but technically the full vector would be the magnitude and direction. So that was worth another 2 points. All total 10 points. Okay, so that was number 1. Number 2 is similar to a couple problems that we did. It's not exactly similar to any one problem in my memory. Maybe there's a textbook problem that we had that was like this. So draw a free body diagram for the mass. So we draw mass M. And we know that there's a tension T2 pulling in this direction. And I can even say an angle. I know that this angle down from this one is going to be this angle from this one to that parallel line. So I could even say that this is theta 2. So I draw a vector that way. Likewise, there's a tension in line 1 that's at a different angle. And I know that this angle here is theta 1. That's that parallel line theorem, parallel axis theorem. I don't know what it's called, but you can figure out that's going to be the angle there. And then we've got the force of gravity. So free body diagram, we draw the forces, not the acceleration. I saw some people just write G pulling down. Well, that's the acceleration due to gravity. It's not the force that gravity is exerting on the mass. for that we have to multiply by the mass. So you would have gotten a point off if you didn't write mass there. So that's it. That was worth 3 points. 3 points, 3 arrows, 3 forces. Assuming the elevator is accelerating now at a rate A, what is this tension in string 1, T1, in terms of mass m and angle theta 1 and theta 2? Okay. So for this one, I would start out with my sum of the forces. F acting on m is going to be the acceleration of that mass. And we know that the acceleration, we don't know which direction it is, but it's going to be up or down because it's an elevator. So for now, I'm going to call y up. And you'll see that we can plug in a negative acceleration later, like we did here, like we do in the next part, and we'll get the right answer. So we can just assume that y is positive. And okay, some of the forces in the y direction, this is the interesting direction. Well, there's 3 components in the y direction. There's the y component of t1, and that's going to be t1 times the sine of theta 1. Why? Well, if I have t1 here, and this is theta, then remember the sine is the opposite, it's the length of this vector, divided by the hypotenuse, and this is ty. So ty divided by the hypotenuse is sine theta. That is equal to sine theta. So ty is equal to t1 sine theta. And t2 is also pointing upwards, so ty is also positive here. So that's t2 sine theta 2, likewise. And then mg is in the opposite direction. And that's going to be equal to the mass times the acceleration a. Okay. Now some of you might have went ahead and solved for t1 here, but keep in mind that you've got t2 in here still, which is an unknown, so you can't solve for it. And we're asking you to solve for t1. And so for that, we need the sum of the forces in the x direction. And I'll show you there, if this is, the y direction is up and x is pointing this way, then, let's see, I need my little piece of tape to know. So I'm not going to go off the rails here. So the x component of t2 is pointing the positive x direction. So I could write t2 sub x. I'm going to skip that step and say that t2x is equal to t2 cosine theta 2. So this is t2x here, the x component of t2, and it's the adjacent over the hypotenuse is equal to cosine theta 2. So therefore t2 times cosine theta 2 is equal to t2x2. So t2 cosine theta 2. Now I've got t1, the x component is pointing in the opposite direction. So likewise, I can write t1 cosine theta 1. And now the mass, that's all of the x components. The mass is not accelerating to the left or right. So this equals ma, which is equal to 0. And so now I've got my 2 equations. My knowns are m, theta 1, theta 2, g and a. And my 2 unknowns are t1 and t2. And I want t1. So the next step is to solve for t2 using the simplest equation, that's this one. So t2, you could do some algebra here. You add t1 cosine theta 1 to both sides, get this on this side, and then divide by cosine theta 2. You'll get cosine, or t1 cosine theta 1 cosine theta 2. And I've done this a lot, so I can do some of these in my head. Some of you, this is still kind of new, so it's okay if that takes a few steps to get to. And now I've plugged that into this equation. I think what I'll go ahead and do is get t1 by itself, simplest, with this equation as it is now. So I'll add mg to both sides. I'm going to get ma plus mg, or mg plus a, minus t2 sine theta 2, divided by sine theta 1. And now I plug in this for T2. So I get T1 is equal to mg plus a minus T1 sine theta 2 cosine theta 1 over cosine theta 2 all over sine theta 1. Okay. Now you could express this in terms of a tangent, so tangent of theta to, but something like this. There's different forms. We accepted them all as long as they only had m theta 1 g and a. You could imagine that we gave you numbers for these. So this was worth 5 points since there was a lot of steps. We make it worth more so that we can give you more partial credit. So if you typed in, or if you wrote in some of the forces, you get a point. And if you wrote some of the forces equals y, and you start off right there, you get another point. Some of the forces there, you get a point. If you figure out this one, you'd get a point. So you see, it's worth more, but there's more opportunities for partial credit. So you should always, if you know how to start, go ahead and do it. And then if you get stuck, then at least you can get partial credit. So this one, let T1 prime be the tension in string 1 when the elevator is moving upwards. So it's moving upwards with a speed of 8 meters a second. So if it's moving, we don't care, right? We don't care if it's already moving. But now we care if it's accelerating, so it's slowing down. So it's moving upwards, but it's slowing down. The acceleration must be opposite the motion. So the acceleration must be in the negative y direction. Oh, then I'd have to solve for T1 here. Okay, I just saw that. So how does this tension compare to the T1 in the string? Let's see. Let's see if I write T1. Maybe I'll complete this. I guess I didn't complete this. Sine theta 1, tan theta 2 cosine theta 2 over mg plus a. I might come back to this later. So in a test, I'm not so sure about this. But I do know that the tension is going to decrease. So the elevator is moving upwards and starting to slow down. And you're going to get a g minus a. So it's going to feel, the mass is going to feel a lower force of gravity. So therefore T1 prime is less than T1. And we could plug in a negative a here and compare it to with a equals 0. And we'll find the same thing. So that was worth 2 points. And if you could just reason your way through it without using the formula, that was fine too. Okay. So on this one, this was exactly like a couple of the problems. So draw a free body diagram for the force on the forces on the crate. Let's say this is mass m, and mass m is 200 kilograms. Well, I know that gravity's working on it. It's not accelerating down or up. Therefore, there must be a force, a normal force, applied by the pickup bed. And then I know that there's going to be a force of friction in here because it's, for one, it's telling me these things, coefficient of friction and stuff. But which way do I point it? Do I point it backwards? Do I point it forwards? Well, what I do is I know that some of the forces in the x direction have to add up so that the acceleration is that way. And there's really only one force that I can think of that would be pointing horizontally, and that's the force of friction. So therefore, the force of friction must be applied this way. And that's it. So it was 3 points for each vector. Minus 1 point if you started drawing in extra vectors. So minus 1 point for each extra vector that you drew. Or minus 1 point if friction was pointing in the wrong direction. Actually, no, we gave you a point here for friction pointing in the right direction. So the way I reasoned it here was sum of the forces in the x direction is equal to ma I hat, and that's equal to force of friction. So force of friction must be in the I-hat direction. So I'd say forward or in I-hat direction. If I say in the I-hat direction, I have to define what I mean is the I-hat direction. So if this is X and that's Y, that nails that down, or I could draw I-hat and J-hat. Okay, the magnitude of the friction force on the crate. Well, here again, we know that the crate does not slide relative to the truck bed, so it's accelerating. Again, some of the force in the X direction is just 1, so it's the force of friction, and that's going to equal mass of the crate times the acceleration, which we know. So the magnitude of the friction force is equal to 200 kilograms, to the mass, times the acceleration, that's 1 meters per second squared. I don't even need a calculator. That's 200 newtons. And that was worth 3 points. So if you could realize this part, even if you just wrote down some of the forces in the X direction equals ma, you'd get a point. I think it depends on how they grade it, but I think you got a point. Now you could start with, I know a lot of you probably started with, well, the frictional force, it's not sliding, so it's going to be mu s times the normal force, and some of the forces in the y direction gives me that mu s is equal to mg. So you could have calculated it this way, but you would have been wrong. So the frictional force is going to be less than or equal to this. If the truck is not accelerating, then there's not going to be any frictional force operating on the grating, or operating on the crate, because if there was, it would just spontaneously accelerate on its own. So this frictional force goes to 0 if the truck isn't accelerating. So this is the maximum frictional force that can be applied without the thing slipping. So this wouldn't have been valid. Although depending on how generous your TA was, he might have given you a point for that just because it's slightly relevant. Okay, now the truck accelerates a lot quicker, 8 meters per second squared. That's almost like it's falling forward because the acceleration due to gravity is 9.8. And the crate slides back on the truck bed. What is the acceleration of the crate relative to the ground? Well, here we can write our same free body diagram. And I've still got these same forces, but now my frictional force, it is sliding, and so now it is equal to the kinetic coefficient of friction times the normal force. And the sum of the forces in the y direction, n minus mg, is now equal to 0. So I know that the normal force is equal to mg. And the sum of the forces in the x direction now is equal to the force due to friction, which is equal to mu k normal force, which I know from here is mu k times mg. Those are my forces. Newton's law says that this is all equal to the mass times the acceleration. So therefore, if I solve for acceleration, my masses cancel, right? I'm just going to write this mg mu k mg times ma, divide both sides by m, those go away. So my acceleration is given by mu k times g. So that's the answer. If you got that, you probably got all the points. We would just plug in 0.15. If you didn't want to actually plug this into your calculator, it's probably okay. Times 9.8 meters per second squared, and this is equal to 1.5 meters per second squared. So if you got that one, that was worth 3 points. And you get points for writing the sum of the forces and going along there. Okay. Now this one kind of surprised me. I tried to say a lot of times that in these types of problems where you have a medium that's moving. So something is propagating through a medium being the air or the water or a moving truck. So something is moving with respect to that medium. What you always do is you're going to add velocities. Sometimes you won't know the two velocities that you're adding, but it's going to involve that type of thing. So an airplane's traveling with a velocity of 150 meters per second due east with respect to the air. So it's pointing east no matter what. So there's east, north, west, south. So it's moving that direction. But the airspeed is moving with respect to the ground at an angle of 50 meters per second north of east. So the air is moving that direction with 50, I'll call that VA, 50 meters a second. And the plane is moving east in the air at 150 meters per second. I'll call that VP. And so we add, what is the speed of the velocity with respect to the ground? Well, V total, vectors. I add these two vectors. And the way I do this is I add the x components. So the x component of the air plus the x component of the plane with respect to the air. That's going to be in the I hat direction. So I'm going to define I hat as east and j hat as north, plus VAY, that's velocity of the airplane with respect to that's the velocity of the air in the y direction, north, plus the velocity of the airplane in the y direction with respect to the air. We know that's 0. So VP only has an x component, so that's 0. VAX, that's going to be VA times the sine of theta, which is 45 degrees, plus PX. Oh, that's maybe I should call it cosine. But call this my angle, theta. Doesn't matter. Sine of 45 degrees is equal to cosine of 45 degrees. Plus the velocity of the airplane in the x direction, so that's all of it. So that's 150. For now, I'll say VP in the I direction. And now my y components, now I'm going to be the y component of the air, that's VA sine 45 degrees, plus the y component of the plane, that's 0. So the speed, we want just the speed, we want the magnitude of this total velocity. So V total is equal to V total x squared plus V total y squared and the square root of all that. So that's Pythagorean's theorem. So V total, if I draw it in a blue pen, is the sum of these, V total. And I've just computed V total x and V total y, and I'll take the squares, sum of the squares. Okay, so we get 150 meters per second plus 50 meters per second for VA times the cosine of 45 degrees. Maybe you'll remember that's 1 over root 2. If you didn't, that's fine. That squared plus 50 meters per second times 1 over the square root of 2, that's sine 45 degrees, and that squared, and that's all square rooted. And if I plug that into my calculator, we should get about 189 meters per second. So that was worth 5 points. What is the heading? Well, once you got this, once you've done this part, that's pretty much all of it. It's just that instead of using this one, you remember V total is now pointing just north of east. That's Vy, V total y. That's V total x. And we want, where's it heading? I can call this theta. 0 degrees is due east, so 90 degrees is due north, so this is kind of what I'm calling theta. That's my heading, so it's asking what's the direction of this velocity vector. So tan theta is equal to opposite over adjacent, so it's V total y over V total x. And let's see, this is going to be equal to 50 meters per second over the square root of 2. So 1 over the square root of 2 is sine 45. And 150 plus 50 divided by the square root of 2, that's my x component, would be tan theta. Turns out this is equal to about 0.19. So theta is equal to the arc tangent or inverse tangent of 0.19. And you get that this is about 10.8 degrees north of east. Okay, so that was worth another 5 points. So you could have picked up a lot of points there if you just knew to add some vectors and weren't quite sure why or how. Okay, now the cannonball problem, this was a lot like Catcher's problem in smart physics. So a cannonball is fired at a wall 450 meters away. We're not saying it hits the wall. We're not saying it hits at the base of the wall. We're not saying it goes over the wall or hits anything. We're just saying it's fired out with this initial velocity at this angle. So theta here is 24 degrees. So the horizontal component of the ball's velocity is this vector here. I even drew it in there for you. So it's V initial x. So V initial in the x direction would be Vi cosine theta. And I'm skipping some steps there. So V initial is in this direction. This is theta. And what we want is the x component, Vix. And then this would be the y component, Viy. And remember, cosine of theta is adjacent over hypotenuse. So it's going to be that Vix magnitude divided by Vi. So Vix is equal to Vi times cosine theta. Well, this is equal to 90 meters per second times the cosine of 24 degrees. And that's equal to 82.2 meters per second. So that was worth 2 points. Now, how long does it take for the ball to reach the wall? Well, there's all kinds of things going. It's going to go up in the air, it's going to come back down. All I know is that it's moving in this direction at 82 meters per second, and it has 450 meters to cover. So I could just use x of t is equal to x naught plus v naught x, I should call this v initial x, times time, plus 1/2 times the acceleration in the x direction times time squared. We're ignoring air, and so there is no acceleration horizontally. So that's 0. And I know that at the end of this time, the thing has traveled 450 meters. And so the time that it takes to travel to the wall, maybe we'll call it TW, that's going to be the distance it's traveled divided by the velocity in that direction. So that's 450 meters divided by 82.2 meters per second. And so this is equal to 5.5 seconds. Now, I don't think this actually occurred, but if you had miscalculated this or something, but knew that you needed the horizontal velocity in that direction and you plugged in the wrong value, I would still give you the points for this, which was 2 points. So I don't punish you for getting the wrong answer twice. That said, I think everybody that got this answer right already also got that answer right. Okay, so what is the maximum height the ball reaches? It is a mistake to think that that is the range of the ball, 450 meters. We never say that the ball falls to the base of the wall. We never say that the ball hits the wall. All we say is it launches at this velocity, at this angle. So really what you got to do is say that you're going to use the y equations now. So y as a function of time is equal to y naught plus v naught y. I'm saying that's v initial y times time minus 1/2 gt squared. I'm going to say plus 1/2 ay t squared. And then ay is equal to negative g. So I've chosen my direction here. I'm saying that y of t is getting bigger. So I've been given some axes. We know that g points in the negative direction, so that's going to be negative. And I'm going to say that y naught is equal to 0. I'm going to define that. So I could figure it out. I got v initial y. I can figure it out from here. It's going to be 90 meters per second times sine 24 degrees times some time. So what is the time? Well, the time is the time that it takes to reach the peak. So how do I figure that out? I figure that out from the y equation for velocity. So if I take the time derivative of this, I get that the y velocity as a function of time is equal to the initial y velocity plus the acceleration times time, so that's minus g times t. And the height, the maximum height the ball reaches, is when the vertical velocity goes to 0. So t at h is when this is true. And if I solve for that, then I get v initial y divided by g. And my initial y velocity is equal to my initial velocity times the sine of the angle. So that's 90 meters per second times the sine of 24 degrees divided by 9.8 meters per second squared. This second crosses out with one of my seconds squared, and the meters cancel out, so I get units of time. And this turns out to be 3.7 seconds. So if you got that far, I'd give you a point. So that's going to say how long does it take to get to the top. Now what I can do is I can plug this in here. By the way, I could also figure out what my initial y velocity was from this. So the initial sine 24 degrees, that comes out to 37 meters per second. I'd give you partial credit if you had that somewhere. You didn't need it to get full credit. Okay, so I know this, and I know the time. So the maximum height, y max, by the way, vy of t is equal to dy dt. So I can calculate this from this, or you could just go to your front and notice that we give that to you. So now y of max is equal to y th. So it's equal to my initial velocity. I'm going to write it out again. The initial sine theta. So this is 37 degrees times the time. So that's 3.7 seconds. So that's times th. Plus 1/2 ay t squared, so that's minus 1/2 g th squared. And if I plug everything in, I know that this is 37 meters per second, and that's 3.7 seconds, minus 1/2 9.8 meters per second squared times 3.7 seconds squared. I get that y max is equal to 68.4 meters. Okay, so that was worth 3 points. And like I said, if you knew that you knew that you needed to calculate the time that it takes to get up to that maximum height, you got a point for that. You'd get a point for figuring out that you need to figure out the initial y component. I think you maybe get a point, partial point, if you knew that you had to use the equation for velocity as a function of time and set it equal to 0. Now it's saying how high above the ground is the ball when it reaches the wall. So for that, we're going to use the same equation, y naught plus VIY t minus 1/2 gt squared, except now we're going to plug in the time that it takes to get to the wall. So at that time, the ball is in the plane of the wall, we can calculate its height. So we're going to calculate y at 5.5 seconds. Y naught is equal to 0. VIY is equal to 37 meters a second, or it's equal to VI sine of theta. So times 5.5 seconds minus 1/2 times 9.8 meters per second squared times 5.5 seconds squared. And this comes out to 53 meters, or thereabouts. So that was worth another 3 points. Okay, last one. So this one was a lot like a homework problem. We had 2 climbers again. So the key is to find that there's two motions. So let's just take one of the climbers and let's generalize things. So they fall from this cliff a distance L, and they're going to accelerate at g over a distance L. And then at this point the rope becomes taut and it starts to decelerate them. So for a distance delta x, or maybe we'll call it delta y, they are going to decelerate to 0. And that's really the whole problem. That's what we're trying to figure out. So a nice thing here would be to just figure it out for one climber and know that the same equation is going to apply for both of them. It'll just be different numbers. So the one to use here, you could use y as a function of time. This is between 0 and t1 seconds. So t1, it falls here in t1, and then between t1 seconds and t2 seconds, it's going to follow another equation with a different acceleration. So it's y naught plus v naught y t plus 1/2 ay t squared. Well, this is going to be equal to g. I'm going to call that 0. So this is really just equal to 1/2 gt squared. Oh, I guess I've made a decision to call this the positive y direction. That's fine. Okay, and then during this time, it's traveled a certain distance. Now it's L, and it's starting out with an initial velocity, isn't it? So now it's fallen a while, and it's starting out with some v initial y. I'll have to figure out what that is. And now we're starting at t1, and now it's going to have a different acceleration. It's going to point upwards. It's going to point opposite its direction of travel, so I'll call that a rope. Okay. So you could do this. Now a shortcut would be to use this other equation. Remember when we're accelerating over a distance and we don't really know what the times we're talking about? This is the useful equation. This just comes from these two equations, the kinematic equations put together. So you could have figured out your way just using these two guys. I'm going to use this one since it's the shorter one. Anytime you've got an acceleration over a distance, over a known distance. This is probably the better one to use. Okay, so here I want to figure out what is my velocity when the rope just becomes taut. So my velocity at time t equals 1 squared is equal to my initial velocity squared. My initial velocity squared is 0 plus 2 times the acceleration over the distance it accelerates. So the acceleration is g, and the distance it accelerates is L. So in both cases, both climbers have a rope of length L. So in both cases, when the rope just becomes taut, starts to become taut, their velocity is going to be equal to the square root of 2gl. Okay, now I'm going to use this equation again. Now there's some other acceleration, which I don't know, that's going to decelerate it. So now my second acceleration, or my second velocity is 0, because it slows to a halt. And my initial velocity is the velocity going into this period where it's starting to decelerate. So that's this one, 2gl squared. So squared, I'm just going to get gl again. Plus my acceleration. Now my acceleration is pointing in the opposite direction. So 2a, the acceleration due to the rope, over the distance. And this is where we get the distance. So we're calling this delta y. So I can figure out what the acceleration due to the rope is. I solve for this. I can add 2ar delta y to both sides, then divide. So I get 2gl, or square root of 2gl squared is 2gl, divided by 2 delta y. And so the acceleration from the rope that Kim feels is equal to gl, the 2's cancel, over the distance over which she feels that deceleration. And the acceleration from the rope that Luis feels is the same thing. It's gl over delta y L. And if I want to know the ratio of Luis's deceleration to Kim's, that's just ARL over ARK. That's GL over delta YL. This is GL over delta YK. Remember, if I have a fraction in the denominator, I take it to the numerator and flip it around. These GL's cancel, and I get delta YK over delta YL. And let's see, this is 1.4 meters, and this is 0.2 meters. So that's equal to 7. So 7 is the answer. That was 4 points. And then I want to know how much acceleration Luis actually feels. So I've got my actual equation here. So let's go G times L over delta YL. So that's 9.8 meters per second squared times the length of the rope. That's 3.2 meters over delta YL. That's 20 centimeters, so 0.2 meters. And if you plug those in, let's see, clear. 9.8 times 3.2 divided by 0.2. See, that's 156.8 meters per second squared. That's fine. We said express your answer in G's. And so this way I could just say, well, it's L over delta YL G's. So it's 3.2 over 0.2. That's 16 G's. That's a lot. I mean, if you got this equation, that's basically the physics, so you probably got all or most of your points for that. So that was worth 6 points, and of course you did most of the work up here. So if you did it up here, we would have been giving you partial credit the whole way. Okay, and that's the test.